Hi, I'm Dingyu Wang. Today I'm going to talk about an interesting line of research of a classic problem called cardinality estimation. This is a joint work with Seth, Pettie, and Longhui. So the problem of cardinality estimation is just the problem of streaming, like counting the number of distinct elements in a streaming set, where you have, the space of your universe is U, and you have a sequence or stream with elements from U, and you want to know the number of distinct elements with just one pass. So the trivial algorithm will be check and count. You just remember what you have seen before and increase the counter if you have seen a new one. So this kind of exact counting, like the count is exact, so you get some absolutely precise answer. But it takes just too much space. You need to remember all the names you have seen, and it just takes linear space. It's too much. Nowadays, data, this number can be huge. So especially in practice, we don't need to know like the exact distinct elements, number of the elements, mostly. And we just need a decent estimation. So the question is, can we, save a lot of space while still give a very precise but not necessarily exact counting? Yes, we can do it. I'll just give you some examples. And the idea is sketching by hashing. So the PCSA is probabilistic counting with stochastic averaging. It's the first probabilistic counting, first sketching ideas for cardinality estimation. For every incoming element, it hashes you to a point between 0 and 1, and it divides the interval into cells with length 1, 1/2, 1/4, 1/8, and so on, and save a bit for each cell. The bit gets 1 if it has a point in it, 0 otherwise. And this is a sketch. So you basically look at your 0, 1 vectors and guess how many points have been in this interval, which is just the number of distinct elements. So in practice, we usually only need the first log U cells. But in theory, you have an infinite. In theory, you have an infinite number of cells and also an infinite number of bits. So Hyperlog log may be currently the most popular cardinality estimation algorithm in practice. The basic setup is the same, but instead of storing a bit for each single cell, it just stores the position of the highest cell that contains any point. So because it stores the position, you just only need log U. So first, note that both sketches are insensitive to duplicates, right? Because, for example, PCSA, if you have if I am an element that has come twice to the sketch, the first time I come in, I get hashed to a point, and it just hits that cell and gets that 1 if it's not 1 yet. The second time I come, it has already been a 1, so it has no effect. The same applies for Hyperlog log. So both sketches are just insensitive to the duplicates and insensitive to the order. You can check this by inspection. So let's say you have 100 points, and no matter what's the identity of those points, assume you have a perfect hash function, and no matter how you in what order or what way of duplicating them while inserting into our sketch, the final distribution of the sketch is already the same. It is only it only depends on the cardinality. So in general, to describe a sketch that do this cardinality estimation job is you can do this with what we call dartboard model, where basically you imagine your hashing space is a square, and you have a lot of cells which forms a partition, and you define a rule that the dots activate the cells. So for each cell, we define 2 states. The first is occupied, and the second is free. And there are 2 rules you need to satisfy to do to count things. first, if a free cell gets hit, it must become occupied. But in the same time, like other cells may become occupied as well. And the second rule is that if you hit an already occupied cell, then nothing happens. You're not. It's like your state has to keep the same as if it didn't come. So an important observation is that once your sketch satisfies these two rules, then your sketch automatically like insensitive to duplicates. So in this dartboard model, like language, in the language of this dartboard model, you can describe PCC sketch as a sketch where, like, let's assume we assume this partition by default. And PCC sketch is just a sketch where you only activate the cell that you hit and do not do anything to other cells. While the hyperlog sketch, you can describe it in this way, where if you hit a cell, you activate that cell if it's free, and you also activate all the free cells that is below you in the same column. So second, let's discuss the notion of mergeability. So we say a sketch is mergeable if for any input sequence A and for any ways of splitting that sequence into two subsequences, there exists a universal merge function. Sorry, the order is reversed. There exists a universal merge function so that for any input sequence A and any two subsequences of A, so that you can merge the subsketch you gain from the two substrings and map the two subsketch to the sketch of the whole string. So if a sketch is mergeable by this definition, then it can be inherently implemented in a distributed setting very naturally. Because imagine you have a string, like a huge string that, if you just process it with a single processor, it will become too slow. What you can do is to split this string into 1,000 substrings, and each substring gets a subsketch. And by the mergeability, you can always have a merge function, just merging one by one, like in general. In general, you can merge all of them into a whole sketch, so that it's as if it has the same distribution of if you didn't do the splitting at all. So, for example, PCC is mergeable. In fact, most classic cardinality estimation algorithm is mergeable. And PCC is mergeable, and you can define its merge function to be this union. So the union is just a cell-wise union. You have same subsketch. After the merging, you get a sketch with the same partition, and each cell gets occupied if it gets occupied in any of the subsketch. So yeah, we like mergeable sketches, but then why do we care about non-mergeable sketches? It may sound a little bit weird, because we want to do things parallelly. The thing is, mergeable sketch usually only allow you to use the double state. By state is just the binary state of each cell as your memory state, and you cannot store anything other than that in order to have a full mergeability. So by that, you then need to come up with estimators of the board and come up with a simple and good estimator is non-trivial, and the analysis of that is also very non-trivial. For me, it seems like quite a lot of effort in the history of this line devotes to the analysis of the estimators. But if you free yourself a little bit, so think about if you allow yourself to store some side information besides the dartboard states, then you can have strictly better estimation at variance. So you can have better estimation. And so today, in our paper, we focus on a style of the mergeable sketch is what we call the martingale transform, which is proposed independently by Cohen and Pin. which is a general way of converting a mergeable sketch into a non-mergeable sketch, while you get an estimator automatically. And in our paper, we established a very complete framework to analyze it. So what is a martingale transform? Well, what does this do to our sketch? To get an intuition, think about this. So, I mean, after those setup, you can consider the problem of cardinality estimation as a time estimation problem, where you have a time and periodically you have dots gets randomly shoot on the board, and the dots just activate the cells in some rules defined by your sketch. And you are an observer. You are time oblivious, so you don't have a fear of time at all. But you can observe the state of the board. And the thing is, you want to estimate the current time depending on the history of the board that you have seen. So imagine you are the observer. You observe the board states as S0, S1, S2. That's the Si is the ith distinct states you observe. So you may want, and you have no idea how long it has passed between those. But you of course, at least you are sure that between each state there's at least one second has passed. Otherwise, it just if no new dots come in, the state will not change. But in fact, an important observation is that you only get jumped into the next state if you hit a free cell. Let's say only if and only if. Because if you hit an occupied cell, nothing happens. And if you hit a free cell, something must happen. The state has to change. So this state jump event is just identical to the event that you hit a free cell. So therefore, the number of elements between each state is exactly a geometric random variable with mean 1 over pi, where pi is just the probability that you are leaving this the current state. Because for each time you just each independent trial, you either leave this state or not, leave this state or not. You try a lot of times until success, a typical geometric random variable. So you can so very natural. So if I want you to estimate how many points have been thrown or how many seconds have been passed, a very natural estimator is just the sum of 1 over pi. And the variance should be about their variance, roughly speaking. So formalizing this intuition, we can define what we call so Tim named this martingale estimator, but we define the retroactive variance. So you can consider this the evolution of this sketch as a Markov chain, where Sk is just the states after you see k elements. So note that this Sk is different from this Sk, because this k is the number of elements, and here this lowercase s0, s1 is the number of your state. So let pk to be the state changing probability. Then we can define the martingale estimator and the retrospective variance. It looks complicated, but if you just look it for 1 more second, it is easy. It's just if the state doesn't change, you do nothing, because you cannot do anything, right? Because while you are in the streaming setting, you even don't know whether things are happening. But if the state change, you increase your estimation by 1 over the probability that it may change. And the same is for variance. So now we are going to establish a framework that analyze this kind of combined martingale sketch. By martingale sketch is so you store the original sketch. But besides that, you store a register for this E lambda, and you just increase it every time you change your state. But this combined sketch makes it non-mergeable. Like there is no way to merge like the martingale estimators of two substreams to form like the martingale estimate of the whole stream. So the first theorem we come up with is we want to characterize the mean of both martingale estimator and the retroselective variance. So the mean is unbiased of this estimator, and this is not new. Like this has already been established by Cohen and Ting, and this is why it is called a martingale, because this minus the true cardinality is a martingale. But what's new is this retrospective variance is also an unbiased estimation of the variance of this martingale estimator, and they mutually have an expression of this, which is cute. So now let's look at a comparison between mergeable and non-mergeable sketch, where so if you look at log-log and martingale log-log, if you compare them like parallelly, you can always do better, like if you allow yourself to be non-mergeable. And especially, and here we then come up with a new mergeable sketch called Carton. And it's a very complicated sketch, which is hard to give any reasonable estimator. But you can use this martingale transform and to use that automatic estimation, because martingale estimator itself is an estimator. And it's all and you can use all the theorems to easily compute its memory variance product. So here the MVP is the memory variance product. And we also prove a lower bound for how good you can do for the memory variance product for the class of martingale transform sketch. It turns out that you can, if you limit yourself with a linearizable sketch, which I will not define like in this talk, but you can check out the paper. Like if you are that kind of sketch, then your MVP is at least H0 over 2. So now I'm going to show you the framework to analyze the variance of the martingale estimator. So first, we only care about the case where the cardinality is large and the number of subsketches is large. So for some notation, we use the Pm, K to be the probability of like the state changing after starting K elements, where M stands for the number of subsketches. So first, we call a symptotic relative variance factor of a class. It's a class of sketch. It's defined as M times the variance of your estimator over lambda times M square. And first taking M to infinity, okay, and then take lambda to infinity. So we say a sketch is scale invariant if first for each lambda, the product of the true cardinality and the remaining area, and the state changing probability converges to some constant, depends on lambda. And if you let lambda go to infinity, and this should converges to some kappa. And for such sketches, we call it scale invariant. And the characterization theorem is as follows. So if you have a sketch that's scale invariant with constant kappa and with some regularity conditions, then your variance factor exists and equals to 1 over 2 times kappa. So this gives a very easy and structural way to analyze martingale sketches. where you first just observe the sketch itself, calculate some property of itself, and calculate on the kappa, and then the variance is just given by 1/2 kappa. For example, PCC and hyperlog log has kappa as 1/log Q and 1/log Q times Q minus 1/Q. And as corollary of the characterization theorem, the variance factor is just 1/2 times this and 1/2 times this. So then I'm going to talk about a truly constant size sketch. Why this is relevant? Because the thing that we cannot propose the difficulty of finding an estimator and analyzing the estimator prevents like this field to propose complicated sketches. But as we say, if you apply the martingale transform and apply that framework, the estimator is given, and the analysis of the estimator is also just routine. Then, given that, we can try wild sketches. So note that GCC sketch and hyperlog log sketch although they have constant entropy for any cardinality, but the number of possible states given cardinality, like as your cardinality goes to infinity, is infinite, the number of possible states. So the question is, can we come up with sketch that always only have a constant number of states and to capture all the cardinality range, assuming we have a free register for the answer? The answer is yes. Consider this. So you still have the basic setup while you just offset it like the even and odd columns a little bit to make it more space efficient. And what you do is, say this is the gray cells. The gray cells are occupied, yellow cells are unoccupied. And instead of storing like the gray cells as PCSA or the highest gray cells as the hyperlog log, you store a Lipschitz profile of the peak. A Lipschitz, I mean, for example, here you require like the point you store between columns are within 2. And once you are doing this, so for example, if you have a new point here, then aside from this becomes gray, so then you just like a curtain, you lift your whole profile up. What's the benefit? The benefit is that because you are Lipschitz, you can store the difference between your columns as a way to store the sketch. And the difference only has 4 states in this case. So in general, we can characterize this whole class as a base Q and difference bound A and number of stored cells per row H. So like this is a very general class of algorithms where H is just how many cells you store from the top. And you can calculate pretty easily. Well, not pretty easily. It's not trivial, but very routinely that you can get the cutoff curtain is this. And therefore the variance is just this. Analysis complete. So now let's see some experiments. So the first is if you use like 128 bits, we compare like hyperlog log and non-mergeable version of log log and the curtain. You see the curtain is more concentrated. And if you use 1.2K bits, and it's just more concentrated and it's more normal. And the thing is, we are the framework characterized as asymptotic variance, but we are kind of curious to know how it works for finite cases. It turns out it's quite good. For example, you see the curtain, both martingale and curtain. The prediction is given by the kappa. You see the variance, and the variance just is very close to the experiment. That's all. Thank you.